change in time.
Yes, E is equal to minus n d phi by dt, del phi by del t, right? So del phi by del t is the change in flux, magnetic flux with time, and n is the number of turns in the coil. So if we change the magnetic flux linked with the coil, then EMF is induced. And why do we put a negative sign in this formula?
Because of Lenz's law, the direction is opposed.
Yes, because direction of induced EMF always opposes the cause producing it. So in Faraday's law was based on electromagnetic induction, right? Faraday's law was based on electromagnetic induction, that whenever there is a change in magnetic flux linked with the coil, EMF is induced in it. And we can use this relation, we can write the relation E is equal to minus n del phi b by del t. And it says that because we have changed the flux linked with the coil and therefore EMF is induced and hence the current is produced in the coil. And because of this current, there is induced magnetic field, because where there is current, there is magnetic field. Current carrying conductor produces magnetic field. We know this, right? So because of this induced current, we have induced magnetic field in the coil. So what are we doing? We are changing the magnetic flux. And how do we change the magnetic flux? There are various ways by which we can change the magnetic flux. What are those? We can change
By
the
increasing,
strength of the magnetic field. We can change the area of the coil placed in the magnetic field, right? We can move the coil back and forth. We can rotate the coil in the magnetic field. So there are various ways by which magnetic flux linked with the coil can be changed. And because of this, EMF is induced, and induced EMF induces the current, and induces current. So induced produces the magnetic field inside the coil, right? So Faraday's law tells us about the magnitude of the induced here, because using this formula, we can find the value of the EMF, right? On the other hand, Lenz's law gives us the direction of the EMF induced and the current. Why do we put a negative sign? This we have discussed in the previous class as well. We put a negative sign because induced EMF so produced always opposes the cause producing it. Induced EMF so produced opposes the cause producing it. Because of which, see, why is the EMF induced? EMF is induced because of the change in the magnetic flux, because of the change in the magnetic lines of force entering the coil, right? If you place a coil in the external magnetic field, this is the, you in your book, the VCE, you will see the word original magnetic field. So original magnetic field is basically the external magnetic field where the coil is placed. Original magnetic field is the external magnetic field where the coil is placed. So these are the lines of force which are entering the coil. So if we have a constant number of lines entering the coil and we are not changing the lines of force, we are not changing the flux, then no current will be induced. Current will be induced only when we either decrease or increase the lines of force. So when we either decrease or increase the lines of force, only then current is induced. Otherwise, no current is induced. So basically we need to change the flux, right? And because of this flux, EMF is induced, and because of the EMF, current is induced. And this current has its own magnetic field, and that magnetic field is the magnetic field induced. We can write like this for this magnetic field. This is your original magnetic field in which the coil is placed. You can use the term original, you can use the term external. But for this magnetic field which is induced in the coil, is the induced magnetic field. So there are two magnetic fields, and these two magnetic fields interact with each other. And this magnetic field has the direction, it opposes the cause producing it. Means if there is a increase in flux, if there is increase in flux linked with the coil, then magnetic field so induced will oppose it, will try to change, will try to decrease it, right? And how does it change? How does it, react? So we'll discuss this in this section. Okay, please write this. Okay. Now look at this chip. What is happening here? We are moving the magnet. Please respond, Manya.
when we're moving the magnet close to the
Coil.
coil, The side is changing to south,
You can see
and
that there
also
is
the
a
current flow
change.
is changing.
There is a change in the direction of current, no, in the coil. So when the magnet was moving towards the coil, then because north pole of the magnet is there, which is moving towards the coil, then you can see the magnetic induced magnetic field has its north there, and it repels it. And when it was moving away, then induced magnetic field has its south there to attract it. नहीं आया.
तो आ गया समझ में.
जब मैग्नेट का नॉर्थ जा रहा है उसकी तरफ जा रहा है अगर, तो यहाँ पे जो कॉइल है, we have this coil here, right? And this magnet is moving towards the coil. So magnetic field so induced, it is like कि वहां पे नॉर्थ ही बन जाए so that उसको रिपेल करे, और जब वो दूर जा रहा है तो यहाँ साउथ बन रहा है कि उसको अट्रैक्ट करे. तो बेसिकली इट इज अपोजिंग द फ्लक्स. So Lenz's law
Okay.
states that the direction of induced electromotive force and the resulting current in a conductor is always such that it opposes the change in the magnetic flux that created it. It is a consequence of the law of conservation of energy dictating that the induced current works against the change. Please take the screenshot of the slide.
Done.
Okay. So let's consider a situation where we have a magnet and a coil. So this is the north pole of the magnet and this is south. Okay? And this magnet is moving towards the coil with some constant velocity, let's say v. And so what is the direction of magnetic flux? See, magnetic field lines emerge from north and goes into south. So magnetic flux entering the coil is this. These lines of force will enter the coil, no? So magnetic flux entering the coil is towards right, no? And because this magnet is moving towards the coil, so number of lines of force entering the coil will increase. So magnetic flux is increasing to the right. It is to the right and it is increasing. Right? Now, because there are more number of lines of force entering, we can see the lines of force are increasing, and therefore there is change in magnetic flux linked with the coil. And because of this change in magnetic flux linked with the coil, EMF is induced. And because of this, current is induced in the coil. And current so induced is in such a way that the magnetic field so generated would oppose the increase in the flux. Okay? So the direction of induced magnetic field would be opposite to the original magnetic field to oppose the change, because lines of force are increasing in the coil. When the magnet is moved towards the coil, then lines of force will increase, and the induced magnetic field will oppose this change, right? So you can see that the yellow lines represents the B induced. These yellow colored lines represents the induced magnetic field. So it will oppose the change like this. तो उसको काउंटर करेगा वो, बैलेंस करने के लिए, क्योंकि इंक्रीज हो रहा है, चेंज हो रहा है, बट चेंज इंक्रीज हो रहा है, तो उसको बैलेंस करेगा, उसके अगेंस्ट जाएगा, राइट? And we can understand this using another way. We have clock face rule that we have read in the previous class, right? In the previous section, I guess, in the fourth section chapter, we had discussed clock face rule. So if the north of the magnet moves towards the coil, then current produced in the coil is anti-clockwise. Why is the current anti-clockwise? Because we know that if the current flows like this, then this side of the coil becomes the north, because current carrying coil produces magnetic field, right? And if the current flows anti-clockwise, then this side of the coil becomes north and the other side becomes south. So in this way, north of the coil would repel the north of magnet. Because it is approaching it, so it is going to repel it. So basically, this is the cause because of which current is induced in this coil, and this coil, the current so induced is opposing the cause. Right? Why is current induced in the coil? Current is induced in the coil because there is change in flux. Right? Because this magnet was moving towards the coil, and so the current is induced. And this coil is opposing the change, because of which इसी की वजह से इसमें करंट इंड्यूस है और ये इसी को अपोज कर रहा है. I hope this part is
इसमें
clear.
मैग्नेटिक फील्ड क्यों इंड्यूस हो रही है?
Because see, initially we have discussed no that if there is a change in magnetic flux linked with the coil, then EMF is induced, and because of the induced EMF, current is produced, and because there is current in the coil, so there is induced magnetic field, because where there is current there is magnetic field. This we know. Current carrying coil produces magnetic field. B is proportional to I. More current, more stronger magnetic field. This we have read in the previous chapter. B is proportional to I, right? Where there is current, there is magnetic field. Yes. So this is the north pole of the magnet. This is south, north, south. So if you move the magnet towards the coil, this we have discussed, right? If you move the magnet towards the coil, the number of field lines entering the coil will increase, flux linked with the coil will increase, and which in turn, what will happen? EMF will be induced in the coil because of the change in flux, current will be induced, and so there is a magnetic field induced in the coil, and this magnetic field opposes the change. So this is the direction of induced magnetic field. Now, because this magnet is moving towards the coil, hence magnetic field so induced is like this. It is against the magnetic field lines entering the coil. It is opposing the change. It is opposing the increase in flux. Right? So how will the current flow? We can find the direction of current using right hand rule.
Right hand rule.
Okay, because magnetic field is in this direction, so current will flow like this. So what is the direction of current? What should be the direction of current? Clockwise or anti-clockwise?
Clockwise.
Why clockwise? Because see, thumb points the direction of, this is how we find the direction of current. Thumb indicates the direction of magnetic field and curling of finger indicates the direction of current, right? So if the magnetic field is in this direction, this is the direction of induced magnetic field, then how will the current flow? Current is flowing anti-clockwise, no? Use your right hand to find the direction.
Okay.
So this is the direction of current, anti-clockwise. Please write this.
So we take the direction of induced magnetic field to find the current.
Yes.
Okay.
Either way, we can we can find the direction of induced current first, and then we can relate it to the induced magnetic field. And or if we have the direction of induced magnetic field already, then we can get the direction of induced current using the same rule, right hand grip rule. We call it right hand grip rule, right? Coil rule.
Yes.
Okay. Second way of doing it is that if this magnet is moving towards the coil with some velocity v, so because this magnet is moving towards the coil, so north pole is approaching the coil. So how will the current flow? Current will flow anti-clockwise. Why? Because if the current flows anti-clockwise, then this face of the coil becomes north, and this face become opposite face of the coil becomes south. So in this way, this coil is going to repel it. Right? So this is the direction of induced magnetic field. See, this time I have first marked the direction of current and later I have marked it for induced magnetic field. In the previous situation, I have first considered the direction of induced magnetic field, then we have got to know about the direction of induced current. Either way we can do it. The thing is that it is going to repel it. So if the current is flowing anti-clockwise because north pole is approaching and current will start flowing anti-clockwise, because anti-clockwise current means north pole. If the current flows anti-clockwise, it implies north pole. This is clock face rule. This we have discussed already in the previous chapter, right? And what if the this magnet is moving away? If this magnet is moving away from the coil, then what? The number of field lines entering the coil will decrease. So phi b, magnetic flux linked with the coil would decrease. EMF will be induced, right? And because now the field lines, are decreasing in the coil. So magnetic field, so induced in the coil would be
It will be less,
it is
and
going to support it because now it is decreasing, so it is going to support it. See, initially because lines of force were increasing, है ना? Lines of force entering the coil were increasing in the previous case. तो इसमें जो मैग्नेटिक फील्ड इंड्यूस हुआ था वो उसने उसको अपोज किया कि नहीं हमें इंक्रीज नहीं करवाना है. नाउ बिकॉज लाइंस ऑफ फोर्स आर डिक्रीजिंग तो ये उसको फेवर में जाएगा. तो लाइंस ऑफ फोर्स बिकॉज आपकी कम हो रही हैं तो जो इंड्यूस्ड मैग्नेटिक फील्ड होगा उसका डायरेक्शन ये होगा. Basically, we want to keep the lines of force entering the coil stable. We are
तो
resisting the
जब वो
change.
डिक्रीज तो जब वो डिक्रीज होगा तो उसकी सेम डायरेक्शन होगी, और इंक्रीज होगा तो ऑपोजिट डायरेक्शन.
Basically, we are resisting the change.
ओके.
Right? If it is increasing, then it will oppose it. And कैसे oppose करेगा? By inducing the magnetic field against it. And if it is decreasing, then it is going to support it by inducing the magnetic field in the same direction where the magnetic field, original magnetic field is. Right? So now how will the current flow? Again, use the same rule. This is the direction of induced magnetic field. How will the current flow?
Clockwise.
Yes, this time it is clockwise. And we can also use clock face rule. So if the magnet is moving away from the coil, so this north is moving away. So to attract this magnet, or to maintain the position of the magnet, how will the induced magnetic field be produced in the coil? Now this time because it is going away, it is receding. So here we need south pole to attract it, right? Because we don't want this magnet to move any further. We want this magnet at the place where it is. बेसिकली ना तो हमें उसको दूर जाने देना है ना उसको हमें पास आने देना है. उसको हमें स्टेबल रखना है उसकी जगह पे, राइट?
यस, तो इसकी डायरेक्शन क्लॉकवाइज होगी.
Now the current will flow clockwise. So if this face of the coil is south, this has to be north. See, you can understand it using this. Any ring you can take. So if you move the finger like this, I'm moving it clockwise. From your side, you'll find it anti-clockwise. If one face is clockwise, other face looks like anti-clockwise. So if this side is clockwise, this has to be anti-clockwise. Right? So one face becomes north, another face becomes south. Clear?
Yes.
Again, because the current is flowing clockwise in this, so clockwise current implies south pole. Which rule we are using here?
Clock face rule.
Yes, we're using clock phase rule here. Is this clear?
Yes.
Okay, let's consider a magnetic field. Cross represents the equally spaced cross.
Uniform magnetic field
Uniform
into the
magnetic field.
page.
Uniform magnetic field into the page. And we have a coil here. And this coil is moving in the magnetic field, into the magnetic field. This is the direction of motion of the coil. So how will the current induce in the coil? See, when the coil moves in the magnetic field, then number of lines of force will increase or decrease.
They will increase.
It will increase. Magnetic flux linked with the coil will increase. EMF will be induced. Current will be induced in the coil. So what should be the direction of current? Because now the number of field lines are increasing. And this coil
Opposite.
is the induced magnetic field is going to oppose the change, right? So what should be the direction of induced magnetic field? If it is
Out of the
downward, then
page.
induced magnetic field should be what is this direction? What are dots
Um,
represent?
Out of the page.
Yes, because your original magnetic field is into the page. No, this is original magnetic field. So your induced magnetic field is in the outward direction to oppose the change. Because when the coil goes into the magnetic field, inside the magnetic field, the number of field lines will increase, flux will increase, and induced magnetic field is going to oppose the change. So what should be the direction of induced current?
Left.
Because now this is the direction of induced
Out
EMF.
of the
See,
page.
we find the direction of induced current by taking the direction of induced magnetic field only. We do not consider the direction of original magnetic field for induced current. We consider the direction of induced magnetic field because we have two different magnetic fields here, right? So we are going to consider the direction of induced magnetic field to get the direction of induced current. I hope this part is clear. So if this coil is closed,
Yes.
then how will the current flow? Like this. So this is anti-clockwise motion. This is the direction of current.
इसमें magnetic field out of the page ऐसे और ऐसे.
Yeah.
Like which way? Okay.
Essay out of the page, and this is the direction of induced current. I hope this is clear. Now let's consider another situation. Now this time again we are taking a uniform magnetic field. So this is your original magnetic field and it is into the page, no? Original magnetic field is into the page. Downward direction. And we have a coil. And now this coil, we are moving this coil away like this from the field. So now the field lines will
Decrease.
field lines linked with the coil will decrease. So induced magnetic field is now in the supportive mode. No? Have you understood? So cross here again, because we are getting crosses here. So it is going to support it because field lines linked with the coil are decreasing now. Right? So this, the direction of induced magnetic field and the direction of original magnetic field in this case is the same into the page. So what should be the direction of current? How will the current flow? Into the page, right? So what is the direction of current? Use the rule, right hand coil rule,
It's
clockwise.
clockwise, yeah.
So current is now flowing clockwise. In the previous section, how was the current flowing? Anti-clockwise. Now it is flowing clockwise. So in this way, we can find the direction of induced current. See, if you get a question based on this, where you have to find the direction of induced current or the direction of induced magnetic field, then you're going to write that question in steps. So what is your first step while writing the solution? First step is you look for the change in phi b. Okay, how is the magnetic flux changing? Whether the magnetic flux is increasing or decreasing, and what is the direction of the magnetic flux? This is the first step that you have to write. Okay, you might have I think you'd shown me one paper where it was written. Ikra has shown. And in step 2, what will you write? In case you get a question like this, so first you have to tell this, that whether the flux is increasing or decreasing and the direction of the magnetic flux, right? Second, you will find the direction of induced magnetic flux, induced magnetic field. Okay? In the second step, you're going to find the direction of induced magnetic field. And from the direction of induced magnetic field, using right hand coil rule, you will get the direction of induced current in the third step. This is how you are supposed to write in your exam. In these 3 steps, you will write the answer. And direction of induced magnetic field and whether it is going to support or oppose the original magnetic field, you can mention it in the second step only. Right? So in these 3 steps, you're expected to answer these kind of questions in your exam. Yeah. Please take the
Yes.
screen. Take the screenshot. So Lenz's law, the fundamental principle means on what basis we use Lenz's law, because it determines the direction of induced current, because Lenz's law states that it opposes the cause producing it, right? EMF induced opposes the cause producing it, because if so induces opposing the cause, and so in this way we can find the direction of induced EMF and hence induced, we can find the direction of induced current, right? Opposition mechanism. So when magnetic flux increases, the current creates an opposing magnetic field. This we have discussed already. If you are increasing the magnetic flux linked with the coil, then current induced in the coil is going to oppose the change in flux or change in magnetic field, and current creates its own field that supports the original flux this way. And because this Lenz's law ensures that energy is not created for free, as one work must be done against the opposing force to induce current. So it links with the law of conservation of energy. And we use Lenz's law in eddy current breaks, AC generators, and metal detectors. We are going to do this AC generators in the next chapter, right? So there are questions based on Lenz's law. You can read the questions, explain Lenz's law and its basis. We know what Lenz's law is and on what basis it works. This we know. Why is Lenz's law consistent with the law of conservation of energy? They ask you this question because if it were not, the induced current would reinforce the magnetic change, creating infinite energy, which is impossible. Thus, the work done in moving a magnet is converted into electrical energy. Next is predict the direction of induced current. We can predict the direction of induced current by finding the direction of induced magnetic field, right? Because if north pole approaches the coil, then the coil face acts as a north pole to repel it. Counterclockwise current, right? And if the south pole approaches, then it acts as south pole to repel it. But if the it is not approaching, it is receding, then what if the magnet is receding instead of approaching?
And then the direction would be same.
Then the pole so created would be like as if it is going to attract it. If the north pole is receding, then the coil, that face of the coil becomes a south to attract it.
Oh, okay.
Yes. If the south pole is receding, then look at me. If the south pole is receding, this is south pole and this is receding, then this face of the coil becomes north to attract it. And if the north pole is receding, then this face of the coil becomes south to attract it. But what if they are approaching? What if north is approaching? Then this becomes north to repel it. What if south is approaching? This becomes south to repel it. Basically, if it is approaching, it is going to repel it. And if it is receding, the coil is going to attract it.
Okay.
It is resisting the change actually. So a metallic rod is allowed to fall freely in a horizontal east-west direction like this. Will there be an EMF induced? If a metallic rod is allowed to fall freely in a horizontal east-west direction, will there be an EMF induced? Yes, because the magnetic field of the earth changes through it, fulfilling the conditions of the law. What is the significance of negative sign in the Faraday's law? Negative sign basically represents the Lenz's law, indicating the opposition.